Hello, everybody. Welcome to the stream. It's another Sunday. We're going to be doing some more game development with Gleam today and a touch of Tiramisu. So I wanted to put on a little challenge for myself and also take a break from the puzzle game. So we are going to try to implement a spline today. If you're not familiar with what splines are curves, parametric curves usually. So they'll be defined within a 2D or 3D or 4D or ND space based on a parameter t, which is like the time from 0 to 1. So you can think of it, it's kind of in that same space as easings in a way, or other kinds of transitions usually go 0 to 1, and that gives you a curve. Now, you usually don't build things with a single spline, you use a sequence of splines. The most common one that people are familiar with is the Bezier spline. So usually the cubic Bezier spline, which has two endpoints and two control points. And the control points, you may have seen it in an editor. It affects the angle of the curve at various positions along that curve. Well, there are lots of other different kinds of splines, and one of them that is, and so like. Let me take a step back. There's this great video, and I'm gonna flip over so we can see it here. You need to go watch this video. It's long, but it's worth it. It's by Freya Holmer, and it's all about the continuity of splines. And when she says continuity, it's a very mathematical definition, but it essentially means how do position, velocity, acceleration, and the other further derivatives, how do they change when you cross points? Thank you very much. Welcome back to the stream. So there are different kinds of splines for different purposes. Obviously, a lot of vector graphics uses Bezier curves, Bezier splines, because they create the sorts of shapes that people want to use when drawing. But Bezier curves are actually really bad for movement. And there's this other kind of spline called a Catmull-Rom spline, which is continuous in at least one of those. It's continuous in at least one of those derivatives that matters for fluid motion. So we're going to use this potentially for camera movement. That might be neat. But I was thinking more of, let's say in the future I want to make like a tower defense game, or maybe have a path finding for a character. And they have to avoid obstacles. What path would they take around those obstacles? Well, Catmull-Rom will give us a really nice, smooth path. And I think that in this example, the neat thing about Catmull-Rom spline is that every point, with the exception of the extra control points at the end, every point the spline passes through. So you don't have additional control points which are kind of off in space redirecting the curve. The essence of it is every point is passed through. So similar to Bezier curves, points ahead of and behind kind of act as control points and affect the spline that's between the 2 points that are interpolated. So so this that's awesome that you made a pathfinding lib. That's complicated on its own, but what you could do is say use a Catmull-Rom spline to animate between the points, the waypoints that you found on your pathfinding. So that would be a way to animate your character through that path. So if you just said, like, I've got an obstacle here, I need to go around it, and I'm over here, and I find a point up here and I find a point over here, and then you could use a Catmull-Rom spline to go from the first point to the last point. Then you kind of have, oh, it's just A star. Yeah. Yeah. You could, now the thing is you could still use this spline. And the reason that we care about this one is that velocity changes are continuous. So in Bezier curves, sometimes what will happen is the velocity, so like the derivative of the position, will go all wonky at the end point of a curve. But since the control points are outside, they're not, you know, Beziers, unless you're doing like S curve type shapes, they tend to be like kind of proximate to the spline. These are like the control points are way out here. And so what you get is that the path through each point stays continuous on velocity. And that's not really the reason. There's a whole lot of math in there that is really interesting. But you can see these are the, I think these are acceleration curves. And I'm not going to play this video, but I do encourage you to go watch it. So let's just advance just a little. Oh, no, don't trigger the ads. Well, regardless, go have a look at that video, The Continuity of Splines by Freya Holmer. She has awesome streams. She does Twitch streaming on her game dev stuff regularly. So, okay, this is the math part. It's not going to be as fun. This is the traditional formulation of the Catmull-Rom spline. So you can see we're going to need to do some matrix mathematics. Not surprising. The Bezier curve can be expressed as a matrix as well, or matrix coefficients. But here, you'll note that the interesting thing about this is you've basically got a cubic formula. You have a bunch of weights across that formula, and then that multiplies by the points. Now, so in the traditional one, you need 2 points beyond the end of the spline, the continuous spline. Yeah, me too. There's going to be math. It's fine. We'll get through it. It's not so bad. But for a lot of computer graphics, they don't use this traditional formulation. They use the centripetal formulation, which only requires 1 point beyond the end of the curve. And so that's this. And this is actually doesn't, this page has warnings on it in Wikipedia. This one does not. Okay, so note here, this is like one spline segment with 4 points. So that's the minimum number you can use for this curve formulation. And they're showing it as a recursive algorithm. So you take you take these points, 0, 0.1, 0.2, 0.3. And this feels a bit like there's a technique for Bezier curves where because the control points in a Bezier curve serve to give you a tangent line, right? So in a cubic Bezier curve, you have 2 control points and 2 endpoints. And the way that you can compute or there's an algorithm similar to this, right? To compute the position on the curve at any t, which is basically you connect, how to phrase it. You use 4 points, and it kind of makes a quadrilateral of sorts, and then you use the t to take a portion along each of those segments, and that gets you down to 3 points, right? And you connect those, and then you have 2 lines, and then you take the t along those, at the same point, and that gives you 1 line, 2 points, right? Hi, Chris. Welcome. We're gonna do splines. And then when you've got 1 line, then you take the t across that, and that gives you the point on the curve. So this is a similar formulation of interpolating the spline. So it's kind of a recursive algorithm. And this is like, I don't remember the name of that algorithm for Bezier splines. I don't know if you do, Chris, but we had to kind of do that for animation in Fable because we use Bezier splines. Should have given the option of Catmull-Roms, but we never got to that. Anyway, so yeah, we can use that. You can use this kind of formulation to compute the spline. Okay, so the knot sequence, I'm not completely clear on what they mean by that, but hopefully we'll get an example down here and we'll be able to see. So, okay, so curve segment C defined by points P0, P1, P2, P3, and knot sequence T0, T1, T2, T3. What do they mean by knots? How are knots distinct from points? Yeah, so uniform. Okay, I guess this is like an interpolation. Hello, Renathias. Welcome. Okay. Well, hopefully we'll go down here and figure out what these knots mean. Okay, so then you take these knots and then you're subtracting. So the curve is T2 minus T. So did you know I'm going to do? That's awesome, Renathias. That'll be great. Okay, so you're okay. So you've built up these factors recursively. P2, P3. Okay, so I guess. Okay, I think what they're saying here is that the knots are where in time space, in the parametric space, each of the points exists. I think that's what that means because that feels a lot like the algorithm that we would use for Bezier, in that it's not like this is 0 to 1 here. This is like 0 to 1 is P0 to P3, right? Assuming that's the space that we're interpolating across. And then you pick the point. So this is like, maybe we have some kind of velocity, some kind of velocity thing here. The interesting thing is, how do we know? Oh, here, they're giving it to us. These are the knots. I was going to say, how do we know what the velocity should be at each point? Okay, so they're saying this is a 2D formulation. I'm wondering if it'll be different for 3D. But so you do. Okay, so T0 is x1 minus x0 squared plus. So it's like it's Pythagorean theorem basically. Okay. And then, for T0, there's this factor is going to be 0. Okay, so that's not so bad. Okay. So for the centripetal Catmull-Rom spline, the value of alpha is 0.5. So I'm guessing that bracket is absolute value. So they take the square root twice for 0.5. Okay, so when alpha is 0, the resulting curve is a standard uniform Catmull-Rom spline. When alpha is 1, it's the chordal. Okay. Now I can see how chordal would be interesting in that you would have that it's like the knots are proportional to the length between the points. But that might introduce some, maybe not, anomaly is not the right word, but I could see why you would want to maybe scale that a little bit, because even though this is even though this is a shorter distance here, note the curve. There's way more curvature here, and it might be relevant to take more time to do the curve than you would think. It might also be awkward depending on the circumstances. So that's why they do a double square root there. Okay. Okay, have first loops and self intersections do not occur. So this is a difference. You can see here, if you've got the uniform, and these are these are the points that it's interpolating through. The uniform is going to have a little loop here, and you might not want that. You might want it to just take a hard turn, right? But if they go like, whoop, I'm going to turn around, and like that has to do with the continuity too, right? In that they've got some velocity going through that point, and then they need to make a quick turn to go back through. And then so the chordal is a bit more like, I'm going to take a wide turn. So that might be more appropriate for like if you're driving a boat, right? This is some like ice skater, figure skater move. Go down here, turn really quick, and then go back through. But you can see how the centripetal actually does really well in that situation. It doesn't make a self intersection. And then like its path through there is a bit more intuitive, right? It's much tighter to the turn than the other two forms. So I could, if we don't want loops or cusps, make a 20-degree turn, somehow keep all velocity. Yeah. Now, I didn't say that velocity had to be constant, just that it's continuous, right? So like, it's possible that as you approach this, it actually slows down, and then you make the turn, and then it speeds back up. It's just not going to, make a quick spin as it goes past the control point, or it goes past the waypoint. Okay, and they have some code in Python. I'm not going to look at that, but we can basically say, like, see here, this is not bad. We'll be able to do that very straightforwardly. Okay, so that's a single spline. Okay. Yeah, so the thing here is I would like this to be both 2D and 3D, so maybe we'll make different versions. And then the chain, let's see here. Sequence of initial points and return the combined curve. Okay. Yeah. The main thing that we'll want in a gaming context is, given a curve, and some progression through time, we'll want to make sure that you can, keep that curve around. Say if your character path or your camera path is going through that, like if you're trying to do a fly through, it seems like a very relevant thing. Then you'll be able to say how much time has elapsed and then make use of all this. So I think that what I want to do, I was worried that we were going to need, given that first formulation, I was worried we were going to need to make a matrix 4 library. Maybe we'll do that later. I don't want to do that today. Let's just make the centripetal. So we're just going to go in here in iTerm, and sorry, that's off screen, but splines. Okay. Zed, quit bugging me about this. I already told you to trust everything. Okay. Okay, so I'm going to make, here's splines. It's not going to do any of that. Nothing to see here. Let's make a splines directory and Catmull-Rom. Okay. All right, we could do the 2D variant first. What I'd eventually like to do here is make an examples directory where we pull in Tiramisu and like draw some of these things, or you know, have a camera. So Chris is asking, I missed the very beginning. Is this a spline library that is going tangentially connected to Tiramisu, or is it for some gameplay mechanic or easy UI? So my original idea for this is that I might use it for pathing or camera control. So the pathing would be like, for example, if I wanted to make either a character move through a world, or perhaps like the path for a tower defense like game. That's my kind of motivation for doing this. And I want it to be in Gleam because it'd be easy to do just like an FFI to JavaScript where people have already written this stuff, and that's fine and all. But we may want to do something else with it. So, yeah. Good question, Chris. Okay, so I don't know what's going to be in here yet. But what I would like to do, I think, is when we construct this, compute. See what we could potentially compute or pre-compute some of these factors, right? So if we have the set and let's go ahead and make it opaque. I think that's worth it. And then let's make new. Let's make a new 2D, right? Because I think that we're going to want a 2D version and a 3D version. I don't know that a 4D version makes sense. Hello, Papa Smarty. Welcome to the stream. Okay, so we need to compute these weights. And I think that the way we might do this is, let's say that this is, these are the points, and this is going to be a list. And let's go ahead and add, say Gleam add a vec, because we're going to use the vec library. It's used in Tiramisu and various other things. This is going to be, and we need to use this. So we're going to have a list of vec2, and I think that we're going to use a result here because it's probably important that we let's import Gleam list. Is that not the thing? Is it list.len? I forget. I've been doing so many different languages lately. Thanks. 40 would make sense for the Bevy Jam theme. Oh, God. That sounds like torture. Oh my gosh. Where's my standard lib? Okay. List length. It is list length. Okay. Okay. We need at least I'll just call it that. We need at least 4 points, right? The interesting thing here is that I would like to express the entire set of curves, right? Oh, that's what he was complaining about, the semicolon. Generic vec2? No, I'm going to use, oh, yeah, thank you. Float. So we need at least 4 points, right? And we'll say to do. And then anything else, we're going to return error nil. And I think that this is, we'll need to make a an error type, but we'll just use nil for now. And then here, we can do all of the stuff. Yeah, Chris, I hear you on the multiple language things. I was writing some JavaScript last week and was like, which for loop syntax is supported in this language? So in the past few weeks, I've done, TypeScript and Go and Rust and Gleam, and sometimes I cannot even remember which syntax is correct for things. And there was a point where I was doing Rust and I was trying to use the colon indexing for slices that the syntax, it says like 0:4 to get the first 4 elements. That's Python, not Rust. Use 0.4. And that was really embarrassing. Life of a polyglot. Okay. Now, actually, let's. I want to inline this. I don't need a freaking guard here. Don't need a guard. So true. This is false. Okay, and eventually we want to return this. Now we need to put some things in it. So let's look at what we need to put in it. We're going to need to put the knots in it. So the knots are just going to be a list of floats. And we'll put the points in there, which is going to be a list of vec2d. And I think that isn't that a type exported by vec2f? There's no types in this module. Why don't they make a type alias? Is it in vec2? Nope. Okay. Oh, okay. That's what it's complaining about. Okay, so the knots, and we'll just put the points in there directly. So we need to compute the knots. and that'll be our, our initialization of this thing. And that's, very straightforward. So what we can do is there a Windows function for lists? Window. List of sliding windows. Perfect. Okay, so we're going to say we're going to compute the knots. And we're going to say list window. I think window by 2, I think is the appropriate thing to do here. And then we're going to fold. Every time, yes! Gosh, you're making me hungry. Is this every time I hear you say knots, I hear garlic knots. Yes, agreed. Okay, so or do we want to do map fold? Yeah, let's do map fold, because what we want to do here is get the, or we could just do fold and say it's a, let's just do fold, because we know the first one is going to be 0 and we'll reverse at the end, as we always do. Okay, so we have accumulator, and then we're going to have a tuple of, and this goes back to our algorithm here. We'll go ahead and close that. Hermite splines are interesting too, by the way. Watch Freya's video. Okay, so we need to take the x component out, square it, the y components out, square it, and then square root, and then power to 0.5, which is just another square root, and then add the previous value. Okay, so the interesting thing here is I think that, well, so if we do windows of 2, we're going to get one fewer element in that list than our original set of points, which is fine. Okay, so we're going to say this is T and T1, except I can't pattern match there. We're going to say this is a pair, and let T, T1 equal pair. And we are going to compute this thing. Except this is not T and T1, this is P and P1. So let's do, we'll do this computation, and then we're going to return T1 and accumulator, like so. Okay, so here we need to do this computation. So we're going to do p1.x minus p2p.x, and we're going to square that. So let's import Gleam float. we're going to use asserts here because and I think that there's a square root. Yep. Let assert and I think that I need to do T0 accumulator here because we want that previous value, right? It's not an integer here. It needs to not be an integer. It needs to be a float. Okay. And because alpha is 0.5, I think we'll just assume that we're going to use this centripetal, right? So alpha is going to be 0.5, which is basically another square root. So we'll do that, x plus y, and S2 is float.square root. There may be a more efficient way to do that. Maybe the answer is pow. Yeah. Let's do pow with 0.25. Math helps you out. Okay. So knots. And then we'll just put it in there. Power. And that helps us find that. Okay. So that's not so bad. And then we can do the same for 3D if we want to do 3D. Yeah. So let's make a new 3D. List effect 3 floats. Okay. Oh yeah, import vec3 type vec3. Okay, and then this we'll do. We'll make a new one, and this is 3D, and this is vec3. And here, so vec3 float. Okay, so we need to do another one in here, which is z. And so let's just do z and plus z. And this needs to be 3D. Okay, so that's basically the same thing, but we've got another dimension on there. Okay. So now, what we should do is let's make an interpolate. And the interesting thing here is, you know, they say recursive. It's not really recursive. There's a limited number of levels, so we can just write these out. Yeah, I mean, they could be like, separate types. I think that's probably reasonable. I mean, we're going to be passing new ones anyway. Let's name it 2D. Yeah, I think that's a good idea. And that's not really parameterized. parameterized and we don't have to. The thing is, though, if we do that, we have to make interpolate method or interpolate functions for every single version. Yeah. And then let's do 3D there. Okay, I'm okay with that. So the other thing here is I don't know that we want to do the uniform versus chordal. Maybe that's something we could do later. Luckily, like a lot of the computations are the same. It would just be a matter of changing the alpha, and that would change the position of the knots. So yeah. Okay, so the challenge with these being lists, I think, rather than... Okay, so let me take a step back. What I might want to do is compute, because this calculation let me see. So I think there's going to be a challenge here in that I want to make a sequence of these splines, right? But this definition is for one spline. So I think that we'll need to find a window of 4 where it's like the first 4 where T3 is greater than the T that you input. And because right now what we have is just all of the points in the entire curve. So like if we've got, well, here we've got 4 points. Let's see if there's another example. Yeah, there's like how to do it and get point at 3. Okay, so they actually do square magnitude. Maybe we can simplify this because we've got the vec2 things. We can do some of this without having to do all these let asserts. Let's have a look at that, the vec2 and the vec3, because we might have something there. So there's like distance squared, which is essentially this, right? And distance does the square root. Distance squared gives us this x plus y. Let's do that. So let's do distance between 2. So this okay. So let's do P1 to P, and then pass that to float power. And that's because this is our alpha. And then we can do the same down here. That'll simplify a lot of things. So no, not compare distance. Distance, thank you. P1 to P, and then pipe that. Okay. That simplifies that significantly, because that's really what we were doing there, right? Basically Pythagorean theorem. Okay. So, not that. We don't need that. Okay, so then they're using a basic lerp, it looks like. Lerp unclamped between K1 and K2 T. And this remap is okay, so they're yeah, I get it. This is doing the A1, A2, A3, B1, B2, and so forth, this kind of progressive this U, the lerping between K1 and K2. Okay. This is actually a pretty understandable algorithm, I think, in this case. Let's see if they do anything different here. Yeah, so when we go to draw this, I was looking at this earlier, and hopefully we'll get to that point that we can draw it by the end of the session. But we can create a bunch of line segments, just give it points. So decide what our interval is going to be, and like how many points to put in the curve, and just draw it with a line in Tiramisu. Should be pretty straightforward. Okay. So, and they don't compute the knots at the beginning, which is interesting. I'm guessing they're making an affordance here for changing the points. Yeah, because the points are public, so they don't compute the knots ahead of time. This is sort of an optimization that we're doing, and not strictly necessary. But I think it will be nice to have that when we go to do the interpolation. So let's go ahead and make let's say get point 2D, and we're going to give it so it's going to be, the curve is going to be a Catmull-Rom 2D, and then T is going to be a float, and this should, we're going to want to make sure that the interesting thing here is that I think T is in units of distance, believe it or not. That would be really useful. Why am I saying that? It's because look how we're defining the next T1 in this sequence of going over windows pairs. We're saying it's a factor of the distance. So it's the T doesn't go from 0 to 1. The T goes from 0 to whatever the length of the curve is. Isn't that interesting? So maybe we don't need to be concerned with clamping it. Because I can conceive of a thing where even if we're doing a square root here, and actually I can just change this to square root. Let's do that up down here too. Okay. So let's do, this is going to be a vec2 of float. The interesting thing is that if we get to where t is greater than the last knot in the curve, there's a question about, do we return something, or maybe let assert okay. I mean, I can actually flatten this. Yeah, thank you. Good call. So I can say let assert okay t1, and then we can get rid of that s. Is that what you were saying? And we can say t1 plus t0. Yeah, that makes it nicer. Let's go down here and do the same. It's not exactly T1 in the formulas, but that's all right. We can just do that. Yep, nice. Okay, so we need to do something like, let's look at the list in standard library. Not there. Here we go. I think window. Yeah, let's do, what we want to find are the, we want to find the four that encompass this. So like, it actually, it's the middle. Is it the middle 2 points? The middle 2 knots. I don't think so, because somebody who knows splines, speak up. But like, you don't plot this P0 to P1. P1 to P2 is the only segment that is computed. So maybe let's start with the assumption that we have only, and we'll adjust this later. What we'll do is we'll make a separate bit that finds the window, and let's just make a, let's say get knots from curve.knots and t, and what this will do right now, and this is knots list of float, t is float, and then this is going to be a return a list of float, and we're just going to do and maybe we'll make it a tuple. Actually, that's probably a good way to do it. Then we can assert that and this is going to be the dummy implementation. Not going to work if t is greater than t3, right? Okay. So then we can go, and we don't even need to let assert there. We can just do this. Okay. So now we can do this computation. Interesting looking at it. I think that there are some pieces that we could pre-compute as well. But if t is greater, I bet you could still go beyond the curve. But for our purposes of making a continuous, like smooth path, we want to pick the 4 that are actually involved in t. So like, what would the input to this look like? It might be you have some velocity or desired velocity of your object. Can I change the Wikipedia to dark? Where do you do that? Oh, here. Dark. Ah, thank you. Okay, good call. So what we might want is, like, we take the delta time from the game loop, right? And we add that to whatever objects progress through its, so we like can multiply that by the velocity and add that to its progress through the curve, and that would be, that input would be the t that goes into where on the curve are we, right? Okay. Yeah. Sorry, my nose is really itchy today. I think it's the weather. Okay, so assuming we have this getNots function, which we'll implement later, we just did the basic, hey, just give me the first 4, which is not going to be always the case. So then we do this stuff. So let's do, and this is going to be really tedious, but we can probably we need to do something like this too. And maybe, like, I don't think that we want t there. What we need is let's just say this returns another one, which is offset. And let's have it return 0. This is not the best, honestly. I'm just coming up with this on the fly. Okay, so then our get points, and we'll do this. Honestly, we don't need that. We just need something from the list module, right? This already exists. We need, this is really easy. Okay, so this is curve.points. And this will be a list, right? Not a tuple, but, and we'll need a let assert there. So we're going to do list.drop offset and list.take 4. Okay. And we'll do that same thing. It might be interesting to have a function that just takes the Catmull-Rom 2D and goes like, given t, slice it out and give me just the things that are in here that are relevant for that t. That would let you like isolate individual curves as well. But for this purpose, I'm not really going to care about it right now. We just need to do the computations now. So let A1 equal, and let's look at that vec2f. I think we just do scalar. Yeah. So scalar and then sum, right? So we're gonna have what do the formulas say? I keep flipping away from it. Okay, so let's do A1, T1 minus T, T minus T0, T1 minus T0. Okay, so they both get the T1 minus T0, which should be T1. Okay, so we are going to do T1 minus T divided by T1. Except we don't know that it's we can't assume that T0 is 0 here, unfortunately. Okay, and then we're going to do vec2f scale. Is that P0? Yep. By that. I'm going to try to make this as reproducible as possible. And we're going to scale P1 by T minus T0 divided by T1 minus T0. And this is the part that's going to be a little bit tedious. My apologies. Looking at the Unity one, what do? They have this remap thing. Interesting that they say it's from 0 to 1. How can they assert that the distances on those vectors don't cause it to go beyond 1? Like this get not interval doesn't clamp, right? If somebody knows the math better. Let me know. Because that confuses me. Yeah, I don't know how they so this remap function may be actually pretty nice to implement. Then we can do, because that takes lerp unclamped, right, which is just going to be Does the vec2f module have a lerp function? Let's project. Not exactly the same thing. Okay. Vec2 doesn't have a lerp. Let's clamp. Not exactly what we want. Yeah, I think I need to make this remap. I'm just going to call it the same thing they did in the C# example. But I'm going to need some kind of lerp that's for floats. And I think that that's going to be pretty key. Stop complaining. There's to do there. Okay, so we're going to do the same thing that they did there, essentially. So we'll take A is a float, B is a float. C is a vec2 float. D is a vec2 float. And U is a float. And it's going to return a vec2 float. I should make my own type alias at this point. Typing that so many times. Okay, so they do lerp. Okay, and so we're going to do U minus A. And this is basically the same thing that we're seeing above. So B minus A. Really uninteresting. I'm very sorry. I thought that these things existed already, but they don't. Or they're in some other library that I haven't pulled in, which is very likely. Okay, T is a float. And this is going to return a vec2d. So this is, you know, we do linear. Let's just Google it because I'm interpolation 2D. What's the easiest? I mean, it's one. Oh, I know what it is. Okay, so it's we're gonna scale A by T. And then we're going to, and I'll combine these in a second. We're going to scale B1 minus T, right? And then we're going to add those together. This, of course, assumes that T is from 0 to 1. The stream being interesting is not, oh, well, thank you, Chris. That's very kind. I feel like it's not interesting because I'm getting frustrated. But am I doing that right? So if we think of it like, the other way to think of it is we could, that's one way, like the typical way you multiply the start point by t and the end point by 1 minus t. But the other way we could think about it is we can get the vector that is the difference. So if we subtract two vectors, we get the vector that would point in the direction from the one endpoint to the other, right? So we could do and then we can scale it by t. Vec2f, thank you. It actually bugs me that those are in different modules, but I understand why. Like, I actually like this formulation a lot better. Knowing your vector math helps here. So now that we have this, I don't know that we need this in any other place. So why don't we inline it up here? So this is actually going to be C and D, except it's actually D and C. And then it's going to be scaled by this. And then we don't need that. Does that make sense to everybody? Okay, now it's just complaining about it's not being used. So let's use it up here as they did. Okay, cool. Thank you. I'm glad it does. So let's go back to their C# implementation here. So lerping unclamped between K1 and K2. Oh, okay. The T is independent of the knots. That's interesting. So what we need here is to compute U. So let's go ahead and do that in their formulation, which is going to be T times T1 right? Okay, remap 2D. And this is, we're going to take A is T0, T1. So those are the knots. And I should actually rename these, I think. Yeah. Can it rename work? Yeah, K0. I think that's going to be easier to remember than trying to translate K to T in my mind every single time. So we're going to have to think about another thing we're going to have to think about here is the T is used to select which knots are involved. If there were only 4 points, I think it would come out to 1. But like you could make the assumption that K0 is 0 if there's only one curve, if there's only one spline. And since we're doing a sequence of splines, excuse me, sequence of connected splines, we will probably want to take let t is equal to t minus k0. So like in the case of the very first spline, it'll just be t. All right. We got 45 minutes. Let's see how much we can get done. Okay. So we get... So that's our lerp. And we're just assuming 0 to 1 for t. Okay, so A1 is remap of K0, and I'm just going to freaking copy this because I can't be bothered to keep flipping back and forth, and I'm sure that that's a little bit irritating for you all as well. This is K2, K3, P2, P3, and A3 is that. Okay, and then they do B1. Goes from, okay, so this is going at a higher level. K2 is K0 to K2 of A1 to A2. Again, this looks so much like the algorithm for computing the Bezier curve, that recursive algorithm. And there we were like, we actually wrote it recursively, if I recall correctly, because it let us make it general. Okay, we're going to say remap 2D, and this is K1 to K2, B1 to B2. So it's interesting there, you can see that like here they're taking each of the individual segments into account, and then they take across points, and then it's like, scope that to the 2 points in the middle. Okay, so the result there is not that useful, but if we have a t that's out of bounds, we'll want to be able to handle that. So I think it's a good time to do a little test with our 2D stuff. Yep. How do we go about testing this? And when I mean test, I don't mean necessarily like write a unit test. That's not what I'm thinking about. I'm thinking about how do we plot this. So maybe what we do over here is let's make an examples directory, and I think that here we want to add Tiramisu as a dev dependency so that we can run an example, or we just make a whole new thing in here. Catmull example. Let's just do that. Okay. So we don't need that directory. Trash it. Trash it, please. And we're not going to do that. Okay. Let's cd catmull example. Gleam add tiramisu. Okay. Oh, did it add it to the top level? Oh, boo. That's not what I wanted. Oh, because I did it in the wrong directory, for Pete's sake. Okay. There we go. Okay. And we're going to Gleam add. Oh, what do we do there? Add dev, yeah. Dev luster dev tools. Yeah. Okay. All right. So, oh, you might want to use vect, dict, ANSI to visualize the curve in the terminal. Yeah. The thing is, though, this feels like a thing where I won't know if it's correct. Unless I'm plotting it. Are you talking about making a plot in the terminal? Oh, you can't. Okay. Yeah, so like I want to be able to oh, and the hard thing here is I looked at this earlier. Savvy doesn't have the like from points thing for geometry. Like there's like points material, which is more like a particles. And what I want is actually, yeah, I want lines. Create line segments. Linear filters. You know, create line material. But like you have to get the geometry for line. Yeah. You can't visualize 3D curve. Yeah, we're only going to do 2D. It's fine. Okay. I should have used mascarpone to initialize this. That's right. That doesn't need, it's that. Okay, and it's going to take, what does it take? It takes init, it takes update, and it takes view. Okay, and start. All right, I need to update the Gleam.toml here. Target is JavaScript. That's probably why it's complaining. Okay, so it takes 4 arguments. Selector. Okay, app. Don't care. Let's look. I'm flailing too much. Let's look. App selector dimensions and bridge. We're just going to do none there. We're not going to bother with luster. So selector is a string. Dimensions is Tiramisu.fullscreen and option.none. Okay. We don't need the let assert. I don't know why this is so hard for me. Okay, so we need an init. And init needs to take a context and returns whatever my model is. We are not going to really do much in terms of that. We're going to make a model, and it's just going to be a unary thing. Okay, so our init takes our model, and what else does it take? Or no, it takes the context. And we don't care about the context yet. Tiramisu context. Okay. And we've got to return model and dispatch. We're going to make a tick message and then option.none. So we have no physics. Okay, and then our update is going to take... It takes the model message and context, okay? And for now, we're just going to return model and effect.none and option.none because we have no physics. So here in the, we need to branch on the message, and let's just go ahead and do that. And we'll throw this in there. That way it's not complaining about that being unused. And we'll do something with the time in a second. What I want to get up here is the view, because that's where we care about it. Okay, if I have a question, if the libtarget is JS, will I be able to use this lib in Erlang? So here's the thing. This example is, but there's nothing about this that says you can't use it on the Erlang platform. Yeah, so if you wanted to do something like do a simulation or something and use one of these curves in it, there's no reason you couldn't do that. It's just that if we want to run Tiramisu, it's only on JavaScript. So, okay. So view takes a model in the context. Okay. And we don't actually care about that model. We don't care about it yet. So this needs to return a scene. So we need to import tiramisu scene. What time are we looking at? 3 o'clock. Okay, so let's do. Let's make this simple. You know, I did this full screen, but I actually think of what I want to do is window back to, and I think I want it just be like square. So we're gonna have to Gleam add vec. Okay, and here we'll import vec to. Yep. So that needs to be a float. Okay. And that'll make it easier when we make our orthographic camera. So let's make a import tiramisu camera. Camera.orthographic. Okay, and what are the parameters to this? So left, actually not orthographic. What's the one that gives you a fixed? Yep, that's what we want. Camera 2D. Zero, zero, center of the screen. Okay. Okay, so that'll give us our first thing that needs to go in there. What does this need? Transform. What is the bool? Oh, active, true. What else is in there? Viewport option none. Okay, camera is C. Viewport is option none. What are we missing? I don't see any problem with that. Expected 6 arguments, got 5. What am I missing? Post-processing. Okay, we don't care about any of that. Okay, so now we have a camera. I think that we should make a plane, which will be the background. Mesh. And we'll just call it background. And that's going to take basic building blocks for, okay. Takes a geometry, material transform, and option. Okay. So option none. Let's just get that out of the way. Okay, it's geometry. We needed to say let bg geo. I think it's let assert. Okay. And we're going to make a tree plane. Yep. Just make it cover the whole screen. Okay. I need to stop looking at the source. I need to look at the docs because the docs will be more helpful. Okay, we did the plane, so let's look at the basic material. Basic color, transparent, opacity. Oops. I don't have that key combo set. Let's just shrink it down. I usually have this key combo that lets me do like upper and lower center sixths, but it's all right. We'll do our best here. Okay, so color. For ease of display, let's make it black. Transparent, false. Actually, let's make it all white. That's easy enough. Opacity is 1. Map is option none. Side is material side. Where's that defined? Let's make it double side. That way we won't get into the situation where we had in the puzzle game where our texture was being rendered on the back side because of the orientation of the camera. Being double-sided is going to be a little bit more expensive to render, but you know, it's a 2D. I'm not concerned about it. Okay. Alpha test 1.0 depth right. False. Okay, so now we can go back to the mesh. Scene. Mesh. So the ID geometry material is BG matte. Transform. We need this to be, so like I think the camera 2D, 0, 0 is the center of the screen. Like, what does it do? Positive Y is up. So does Z go into the screen or not? Does it grow? Or is, like, because look at this, 0, 0, 5. And I'm guessing it's looking at 0, 0, 0. Okay. Well, let's adjust this. The camera. Let's use identity for the background. And because this is white, We should be able to see this before we even get a curve on here. So it might be worth going Gleam run luster dev start. Did I import it twice? I did. Okay. Okay. So let's inspect this and make sure that we got app and it's not it's not getting loaded on there. And I think we're only getting white there because, like, there's no canvas in here. We're only getting white because that's the default. All right. Let's see. I try to erase that from my history, but it keeps popping up. Let's see what the like one of the simple examples. See camera 2D. I want to make sure we're not making this stupid. I just return nil. Okay. Here though, it's saying full screen, but it's mapping the canvas size to the camera. We'll look real quick. See, make sure I'm not diverging from this too much. Oh, okay. I need to add this to our gleam.toml. And then we'll restart. Because I think that's like, we need to import this is a little bit that mascarpone would do for you automatically. That's why it was like, hey, you're not loading anything. Okay, so now we're like, let's look at the elements. Okay, so we're getting the app, we're getting the canvas with 600 by 600. So we should be rendering a black, nothing special in the console. We should be rendering a black square on there. So yep. Yeah, it's so bright. I'm very sorry. Here, let's tone that down a little bit. Okay, background color black. That'll make things a little bit easier. Okay. Yeah, except we need to restart. Okay, so now it's actually just showing a white canvas. So the interesting thing here is we're not getting the background. Oh, well, the background's white, so we actually are rendering it. Let's turn it red. Yeah, okay, so it is rendering that. It just turned out to be white. That's fine. Let's make it a medium gray and then move on. Okay, because what I want to do is draw on here our curve. So we know that. Let's make a curve. And what we need to do is add splines. That's how you do it. Fine, I don't actually care. That's just a warning. Okay, so we're going to import splines, Catmull-Rom, and Catmull-Rom 2D is the type, and we want to get, yeah, let's start with that. Okay, it finds that type, so we're fine. Okay, so we can say Catmull-Rom new 2D, and we need to give it a list of points. So I think what might be interesting is so 0, 0 is in the center. Let's start at like we're going to start at negative 250, negative 250. And then let's go over into this quadrant. So let's do, let's go to positive 125 and negative 200, so we get a little interest. And then we're going to turn, we'll go up to this quadrant, and then we'll go to this quadrant. And that should be enough. The interesting thing is that only, let's actually maybe do one here at 0 and negative 225, because we need a control point, right? Maybe we can start with this one segment because we don't actually care about the rest of it. So it's kind of going to go like that, and then let's have it go upward on the end. So 200 and okay, this is not going to be particularly interesting. So we're going to say let assert okay is that, and C. Okay, easy enough. So we did that because we made the API return result. It doesn't have to, but for this is good enough to define a curve. I don't know that this curve is any good or interesting, but now what we can do, and we're gonna have to write a little bit of FFI, I think, to be able to get the geometry. So let's go. Let's go. Let's call it line geometry from points. And this is going to be, points is going to be a list of vec2 float. And this is going to be Savoy, and we're going to have to import Savoyardi, which I never remember. Savoyardi. Okay. Okay. Thank you. Autocomplete. Oh, wait, can I do that? Do I even need to do that? Center. It's just geometry though. And this is going to be, we're going to make an external JavaScript. And this is going to be, we'll just put it in the same directory. Catmull example.ffi.mjs. And then we're going to make a function that says, we're just going to call it line geometry from points. The reason I want to do this is, yeah, I know you're not used. Okay. I want to be able to call the Chef Boyardee. Savoyardi, Chef Boyardee. They're not that far. They're not that far off. That's a good one, Chris. Okay. So I wanted to use the 3.js, and we're going to have to pop it back up here. What I want to do is buffer geometry. And there's a thing where you can do, I looked it up earlier. Set from points. It was either that or it was like, it was on the line stuff. Line geometry. Okay, yeah, so you construct a line geometry and you say geometry set from points. Must be at, oh, imported directly. I guess if you're in 2D space, it assumes 0 for the Z. I hope this has the add-on. Okay, so instance buffer geometry, line segments geometry. Here, regardless, we're gonna have to do. We're gonna have to do it like Savi already does. How about that? It already knows. Because it's all down in here, isn't it? Somewhere. Anyway. Actually, I want to see what Zoe already does for its imports. Yeah, it uses the like that. That's what I want to do. I wonder. I bet I could import this line geometry. Could give it a shot. If it's not there, it's not there, right? Okay, so the we're just going to do that. So that's what we're gonna. Okay, const geometry is line. I don't know why it's like that. It's line geometry. Let's try line. Do that. That's just weird. Okay. We'll say new and geometry set from points. Okay, doesn't like that. Array points. Return geometry. Yeah, I don't know if that's going to work. I don't know if this add-on is included. From line. I don't care about setting the colors or positions. Set from points is really what I want. So what we're going to do here is we're going to yeah, of course it's never used. Okay, so we're going to create a, let's create a basic material first. And we need to look at the, not that. Let's look at the material. Is it material? Yeah, so let's make a line material. Okay, and we're gonna make a color, and let's make it red. Gonna look great on that dark gray, on that medium gray background. And then the line width is let's make it 5. Okay. Because we're doing 600 by 600. Okay. So now we need the actual geometry of it. And let's do we're going to say that this is going to return we actually need a tiramisu geometry, which is just like custom geometry. So we're going to take the curve. Okay, and then what we're going to do is we're going to generate a bunch of points, right? And then we're going to pass it to that. So we need to loop, a certain number of times. So we could say let's look at like map fold or something. I kind of want to like generate a list and then like, because I want to get a certain number of times. One thing that Gleam does not help you do is build that kind of loop. Like if I were in Elixir, I'd probably make a range and then use that as an enumerable and iterate over that. But there was even like a times function, I think, that would give you a range. Let's just start with 10. This is dumb, but we're okay with doing dumb. Dumb is fine. Okay, and then we're going to map that. And except I'm going to do this. Let's just make them the intervals that we care about. And if we want more intervals, except that's going to be 1.0. So those are the intervals, and it's not going to be smooth, right? Because we're doing only 10 segments. So let's list map that into with. So Catmull-Rom get point 2D, and we'll pass the curve. And can I get an underscore, please? Okay. Okay, and then we're going to pass that to line geometry from points. And then we'll pass that to geometry.custom. Okay. We need to do that. Okay, so let's go back up here, and I'm sorry that took forever. We're going to make a curve geometry. And then let's do scene.mesh. And the geometry is going to be our curve geometry. The material is going to be our line material, curve material. Yep. Our transform is going to be identity. And we might need to adjust that if we can't see it. And physics is going to be none. Okay. Oh, I'm not running. Okay, so let's have a look at this. Something is wrong. Okay, so it's not adding. Okay, so 3 add-ons does not provide. So we're going to need to look into where that is, if it's even available. I don't know why it's named like that in the. Okay, so fine. Okay, so we can't see it. So let's translate it. It's probably colliding with this. So let's transform at 0, 0, and 1. So it's higher. Okay, so we're not seeing it. A scene inspector here would be really interesting. Where's the debugger? Let me pause this. Okay, so let's just look at one of these. And see what we've got in there. Line geometry. Okay. Yeah. Hey, at least you can see the, yeah, you can see the UID is changing. I don't know that that's a good thing. It's supposed to do scene diffing and all that, but the interesting thing here is it may be splitting the You know, let's do something different rather than um, echoing out the scene graph. Let's echo the curve. Okay, so there's our points. Look at the T. That's really interesting, or on the knots. So let's stop echoing that. And let's do what N and B suggested earlier, which is echo the points. And not actually that. Let's do it here, because that's going to repeat and not here. Okay. So those are really curious. Our original, yeah, so it's going to be between x0, y negative 225, and x 125, y negative 200, and I think that we're getting the wrong results there. And it could be that, note that it ends with 0, 0. That's really curious. Okay. Let's take the echo out of that. Let's throw it in here. Where would we put it? Yeah, that's really curious, especially like this 0, 0 at the end is super suspicious. It makes me wonder what's going on there. It's possible we have a little tiny bug in here. But hey, this was interesting. Did some math. Didn't quite get it displaying on screen, but we can see, you know, taking 10 samples out of that range, what we got. And I think we have some math to fix. So we'll maybe look at that again next time. Thank you all for hanging out and giving me feedback in the chat. It was great. And we'll see you next week.